All right, we are recording. So, any questions? Yes.
Okay, can you go over the greatest eastern elongation, like the inferior conjunction?
Yeah, all that goodness.
Yeah.
Okay. So,
Chapter 3 at the bottom.
yeah, I just gotta, are you talking about where the slide is?
No, I'm just talking about where it's on
Okay,
this.
'cause that's what I'm trying to find is, here we go. Here's the slide right here. So this is, we've got both an inferior planet, in particular the one they've drawn there is Venus, and then there's a superior planet, which they've chosen Jupiter for. It doesn't really matter, it's certainly not to scale or anything like that. So for superior planets, there's only two kind of big events. There is conjunction and opposition. Conjunction in general means when two things are close together in the sky. Not close together in space necessarily, but just in nearly the same direction on the sky. And for the planets, conjunction, you can talk about like a conjunction of Mars and Venus, which would mean Mars and Venus were close to one another on the sky. What we're doing here is conjunction with the sun. So with a superior planet, one further away from the sun and Earth, there is conjunction with the sun. That's when it is very close to the sun in the sky. It usually doesn't pass directly behind it, but that doesn't matter in terms of, are you going to be able to see the planet when it's in conjunction with the sun? Like, can you go outside and see it in a situation? No, because, the sun is right there too. And so it's up during the day and just being completely obliterated by the light of the sun. So it's on the far side of the sun from the Earth when it's at conjunction. And the opposite of that is opposition when it's on the opposite side of Earth from the sun. So in our sky, when the planet is at conjunction, is at opposition, that's like, what phase of the moon is in opposition with the sun? Opposite the sun. What phase of the moon is it when it's opposite from the sun in the sky? Full. Yeah, that's like a full moon. So a planet at opposition does the same thing the full moon does. In other words, it rises when the sun is setting, it sets when the sun is rising because it's on the other side of the sky from the sun. And so, in other words, here's Jupiter, here's the sun. So if we're on Earth, when we point to the sun, we have to point the other direction to get to Jupiter. So does that make sense?
So anything further away from the sun than Earth is superior?
Yes.
So all the Jovian planets are superior?
All the Jovian planets are superior. What other planet is superior? Mars. Yeah.
Okay.
So Mars and the Jovian planets are all superior planets. And it's not a hierarchy, in other words, being further from the sun doesn't make you better. It's not like Mars is better than us. It just means further from the sun.
So then what about the elongations?
So so only inferior planets have elongations because the point being, the elongation is when it's as far from the sun as possible in the sky. An inferior planet can only get so far from the sun in the sky because it's orbiting closer to the sun than we are. Whereas a superior planet can get all the way to 180 degrees away from the sun in the sky.
Okay.
But can Venus ever be on the opposite side of the sky from the sun? No, because to be at opposition, the planet has to be further from the sun than we are, so that it can be on the opposite side of the sun for us. So for an inferior planet, they can only get so far away from the sun in the sky in terms of the angle, and those are at the so-called elongations. Or in other words, if I make the approximation that the orbit of the planet is circular, which is not a bad approximation, especially for Venus, if like this is Earth, and then let's say this is Venus's orbit. So if you think about it, the times of elongation, and then here's the sun in here, the time of elongation is going to be when a line from Earth to the orbit of the planet is just tangent to it like that. So in other words, you need Venus to be here, or alternatively, relative to Earth, here in its orbit to be at elongation. In other words, for the angle between the sun and the planet in our sky to be as big as possible. Because if I imagine following Venus along in its orbit, here it is at, so then I didn't mention, but there's also two conjunctions for an inferior planet. There is inferior conjunction when it's between us and the sun, and superior conjunction when it's on the other side of us from the sun.
So it's all in relativity to Earth then?
It's relative to Earth. Yeah, this is all relative to Earth. If you lived on Venus, Earth would be a superior planet. It could come to opposition and conjunction.
Okay.
If you lived on Mars, Earth would be an inferior planet, and so Mars sees Earth having the greatest eastern and western elongations, and an inferior and a superior conjunction. Notice, when Jupiter is at opposition as far as Earth is concerned, what would Jupiter say about Earth? Earth is at inferior conjunction, right? From Jupiter's point of view, when we are at opposition, when Jupiter is at opposition from our point of view, other side of the sky from the sun, Jupiter sees us in between it and the sun. So opposition of Jupiter corresponds to inferior conjunction of Earth as seen from Jupiter.
So is opposition more for the Jovian planets
And also
Mars. And
It's
then
for superior planets. Opposition only happens for superior planets. Yes.
Okay, and then conjunction only happens for.
No, conjunction happens for every planet.
Okay.
So for superior planets, there's only just one kind of conjunction, namely it's on the far side of the sun.
Okay.
For inferior planets, they can be on the near side of the sun and in conjunction with it. That's superior conjunction, inferior conjunction, and they can be on the far side of the sun from us, and that's superior conjunction.
Okay.
Now, notice, of course, Earth is moving the whole time, so in other words, really Venus would be at different parts of its orbit between the two conjunctions, but yes.
So it's just our perspective of wherever we are.
It's just our perspective. It's relative to wherever we are. It's how we are seeing the planet. It's not, there's not a place in the planet's orbit where it's always at inferior conjunction.
Yeah.
It's a combination of where we are and where the planet is.
So
And I'm sorry, go ahead.
I'm sorry, so you can think of, I'm just trying to think of a way to remember. So like inferior conjunction is when it's closest to us in between the sun, and superior is farther away.
Farther away. Just think of inferior is closer and
As in,
superior is
yeah.
farther. So inferior planets are closer to the sun. Inferior conjunction is when it's in between us and the sun versus on the far side of the sun.
Can you repeat that? What was the last bit?
I don't know. What did I
You're
say?
saying inferior is like in between us and the sun, and superior
Right. For
is
conjunction, inferior is in between us and the sun. Superior, here, it's funny terminology, but superior conjunction for an inferior planet is when it's on the far side of the sun. So I don't know. You might think, again, I come up with silly mnemonics all the time. What's the name of what's the abbreviation for the International Space Station? The International Space Station. It's not going to work if you don't think. ISS is the International Space Station. ISS, inferior, sun, superior, something like that.
Oh, wow.
You know.
That was good.
Okay, you like that?
Yes.
Think of it?
elongation. Oh, she's my greatest Western.
ISS, inferior.
What's the relevance? What's the use of an elongation?
It's so at elongation. So, for example, right now Venus is visible in the evening sky. If you go out at sunset, you can see Venus in the evening sky. Now, let's say here is the setting sun, right? So Venus is orbiting the sun, right? And so at conjunction, Venus is very close to the sun in the sky. Occasionally, it's even behind it. So you're going to have a hard time seeing it. But then Venus, as it's on the far side of the sun in its orbit, it starts swinging around and getting further from the, if I do this in 3 dimensions, Venus is going like this as far as we see it. It's literally tracing a circle around the sun. And so that angle from the sun to Venus keeps changing. So in other words, here, when Venus is at inferior conjunction, continues along in its orbit relative to us, notice that the angle from the sun to Venus keeps opening up, opening up, opening up. It hits a maximum. It hits a maximum right here at the greatest, this would be the greatest, this would be the greatest eastern elongation. And then as it continues around its orbit towards superior conjunction, it's getting closer and closer to the sun in the sky again. And then it swings around, and at this elongation, it is its maximum angle from the sun again, and then it gets closer to the sun again. I hope I said it right. Sorry, that's greatest western elongation. Yeah. Right, okay. So, what we see in the sky then is if you go out every evening, you see Venus getting, when it's on the far side of the sun and starts coming around the bend, so to speak, it starts to get further from the sun in the sky. What that means in a practical sense is you go out at night, and from night to night to night, it keeps getting further and further above the horizon at sunset. But there's a maximum angle that it makes from the sun in our sky, about 47 degrees it turns out. Venus can never be more than 47 degrees from the sun in our sky. And then the angle starts closing down again because it's rounded the bend past the elongation and it's getting towards conjunction again. So in practical terms, the elongation is when the planet is as far from the sun in our sky as it can get, is what it comes down to.
It's almost like our horizon.
I wouldn't call it our horizon, but it's when the planet gets as far from the horizon, almost. It's literally it's just the angle from the planet to the sun in the sky. So in other words, another way to put it is the time that it's easiest to see the planet is when it's at its elongations, because it's as far from the sun as possible in the sky. So it'll set typically around the latest at that point. It'll be visible longer after sunset or before sunrise or whatever. And so it relates to the planet's visibility to us. Mercury orbits closer to the sun than Venus does, and as a result, Mercury's hard to catch, Mercury's hard to see, because it's never very far from the sun in the sky. So even at its elongations, it's not that far from the sun in the sky. Plus it whips around the sun. It only takes 88 days to go once around the sun. And so I've only seen Mercury a few times in my life because of the fact that it's always close to the sun in the sky, so you have to catch it. So recently, it was visible recently.
Thank you.
Yes?
This is going to Newton. So the understanding Newton's universal law of gravitation, could you just go over like an example of that?
Yeah, so first of all, what the law says is that if I have two masses that are spherical, like, planets or whatever, and they have a certain distance between them, they're each pulling on each other via gravity. Each one is tugging on the other via gravity. And there's this formula that says there's this number that's the same everywhere in the universe, called big G. And then you multiply the two masses of the planets together, or the planet and the star, or whatever the two bodies are, divide by the distance squared between them. And it obeys Newton's third law. In other words, both of them are pulling on one another. Each pulls the other towards it, and they each pull one another with the same amount of force. Notice this is the force that each one of them feels. So that's illustrated in this figure by drawing two equal length arrows that are pointing in opposite directions. So I'm pulling on you via gravity, you're pulling on me via gravity, we're pulling on each other equally hard. And so that applies in our solar system, for example, where consider Venus and the sun. Okay? I'm going to ask you a trick question. Which force is bigger? The force of gravity that the sun puts on Venus, or the force of gravity that Venus puts on the sun? They're the same, right? That's why it's a trick question. Equal and opposite, right?
Bonus point?
Bonus point, right? Yeah, right. Bonus brownie point. Okay. Yes. So
if there's an
how,
object between them, the sun will pull on it more.
yeah, if there was an object between them, then both Venus and the sun are pulling on it. But in that case, unless it's really close to Venus, the sun is pulling on it more. Yeah, that's absolutely right. You're remembering a lecture tutorial from last semester, I'm going to say there. Because we did some with like planets in between Mars and Earth, and I mean a satellite in between Mars and Earth and all that. Yeah, but yeah, you're right. If there's like something halfway between the sun and Venus, the sun's pulling on that other object way harder than Venus is. Yes, absolutely. And so how come then, if Venus and the sun are pulling equally hard on one another, why does Venus move so much more than the sun does?
The acceleration is different.
The acceleration is very different because,
Sun exerting greater force.
no, careful, they're exerting equal forces on one another. I'm talking Venus and the sun, not on a third object here. I'm talking about Venus and the sun, the forces that they exert on one another.
Isn't it just the mass?
Yeah, the masses are very different. The sun is way more massive than Venus is, so for the same amount of force, Venus has a lot more acceleration than the sun does. So in other words, the reason why we say the planets go around the sun is because the sun is so massive that it doesn't move very much. It is moving. It's not really true the planets are going around the sun. What's really true is the sun and the planets are all going around what's called the barycenter of the solar system, the center of mass of the sun and planets. But the sun is so much more massive than the planets that the amount that it moves, the size of its orbit, is way smaller than the orbits of the planets, and so it's a good approximation to say the planets are going around the sun, because that's almost the same as going around the barycenter, which is actually close to the sun, since it's so much more massive than all the other planets are.
So on the example we talked in class with like the bug and the truck.
Yep. Mm-hmm.
So like the masses don't matter in that, the acceleration matters?
No, the masses matter because the acceleration is the force divided by the mass. So in other words, those two things are tied to one another. Acceleration is force divided by the mass. So if each one has the same force on it, the one with the smaller mass down there in the denominator is going to have a much bigger acceleration. So the bug and the truck, when they collide, put equal and opposite forces on one another. But when I take that force and divide it by the mass of the truck, I get a small number for the acceleration. When I take that force and divide it by the mass of the bug, I get a squished bug. I get a big number for the acceleration.
Okay.
I have a quick question.
Yeah.
So, understand how the temperature of a substance is related to the motions of its constituent atoms. No absolute zero represents, and how to represent Kelvin. Is it just simple to say absolute zero, nothing can move, no life can exist, and it's just represented as 0 Kelvin?
So 0 Kelvin, you're on the right track. 0 Kelvin would mean, so we have to be careful. Before we understood what's called quantum mechanics, then we thought 0 Kelvin would mean no molecular motion whatsoever. Everything would be motionless. Now we realize quantum mechanics puts a minimum on how much energy, how much motion energy things can have. So 0 Kelvin is when there is as little kinetic energy of motion of the atoms and molecules as possible. It's not 0, but it's as small as it can possibly be, is 0 Kelvin. And any warmer temperature, the atoms and whatever are jiggling faster. If you were moving around in a gas, they're flying around, smacking into one another. In a solid, they're jiggling back and forth. In a liquid, they're also flying around, smacking into one another. In any case, those microscopic motions every which way are faster as you make the temperature higher, is what it comes down to. If you heat up an iron skillet, the iron atoms are jiggling back and forth on a microscopic scale faster when the skillet is hotter. If I heat up the air in this room, the molecules are moving around faster, slamming into one another as the temperature increases.
Thank you.
Yes?
Can you go through what uniform circular motion is and the analogy with the ball being spun around in a circle?
Yeah, so uniform circular motion means motion in a circle at constant speed.
Okay.
That's all that means. So in other words, if you are riding a horse on a merry-go-round, you are moving in uniform circular motion as long as the merry-go-round is spinning at a constant rate. And the significance for us in terms of planetary motion is we can make a nice analogy with, so first of all, if something is moving in uniform circular motion, is it accelerating?
Yes, it's constantly changing direction.
It is, right, because it's constantly changing the direction that it's moving. And remember that while the speed is constant, there's more to velocity than how fast you're going. Velocity involves not only how fast you're going, but also the direction you're moving. And any change in velocity is acceleration. And since velocity contains both direction and speed, that means if you change your speed, yes, you're accelerating. But also if you change the direction or you're moving, yes, you are accelerating. So in uniform circular motion, there is acceleration. If there's acceleration, that means a force is needed to make it happen, right? That's Newton's second law, or first law for that matter. If something is accelerating, a force is needed to make it happen. And the intuitive way to understand the direction that the force needs to be in uniform circular motion that I like to always talk about is pick up little sister or little brother, swing little sister around in a circle, and I think you can imagine you need to be pulling inwards on little sister, otherwise she's going to fly off, okay? So if you need to be pulling inwards on little sister, that means that the force needs to be towards the center in the uniform circular motion. You need a force towards the center to maintain uniform circular motion, a centripetal force we call it, a center-directed force.
And that would be the sun.
Right, so that's the analogy we make. The guy here is swinging a ball around on a string, okay? The tension in the string provides a center-directed force that keeps the ball moving on that circle. Now consider a planet going around the sun in a circular orbit. So there's no string anymore, but there's still something that's providing a force towards the sun. What is that? It's the sun's gravity. The sun's gravity pulling the planet towards the sun is a force pointed towards the center of the orbit. That is the centripetal force, the center-directed force that is holding the planet in its motion. Now, of course, a real planet orbit isn't a perfect circle, but it's still true that it is maintained in its elliptical orbit by the gravitational force of the sun. The force is always towards the sun as the planet or comet or whatever moves on its orbit, whether that's a circle or whether it's an ellipse. Now, if it's a circle, it maintains a constant speed because it turns out that's what you expect when the force and the velocity are perpendicular to one another. But when they're not, you get changes in speed. So for example, here we've got the comet, let's say, or planet. Well, it says planet here, so I'll say planet. Here's the planet. On this part of its elliptical orbit, it's moving in the direction of the red arrow. The sun is pulling towards itself, the gravity in the direction of the blue arrow. So notice that there is a component of the force from the sun that is opposite the direction that the planet is moving at that instant.